Our Sun, along with the entire solar system, is not stationary in space. Instead, it's on a grand journey, moving around the center of the Milky Way galaxy. This journey is often described as one complete orbit around the galactic center, a cycle that takes an immense amount of time. This is what's known as a cosmic year or a galactic year. To put it into perspective, the Milky Way is a vast spiral galaxy containing hundreds of billions of stars spread out in a flat, rotating disk. The Sun lies roughly 27,000 light-years away from the galactic center, nestled within one of the galaxy's many spiral arms, the Orion Arm. As the galaxy spins, the Sun travels around the center, weaving through space at an average speed of about 828,000 kilometers per hour, around 514,000 miles per hour. Yet, despite this phenomenal speed, it takes the Sun roughly 225 to 250 million Earth years to complete a single revolution around the Milky Way's center. This length of time is staggering when compared to the 365-day orbit Earth makes around the Sun. To offer a clearer comparison, since the Sun formed about 4.6 billion years ago, it has completed approximately 20 to 25 such galactic orbits in its lifetime. The idea of a cosmic year introduces a scale of time that is almost beyond everyday human comprehension, stretching back to periods long before the rise of complex life on Earth. In fact, the timescales involved make it a useful concept for astronomers and geologists alike, placing Earth's history within the broader context of galactic movements. What exactly is happening to the Sun, along with the solar system and everything bound to it, as it moves through the galaxy during one cosmic year? The journey is more dynamic and complex than a simple circular orbit might suggest. The path is not a perfect circle. Instead, the Sun travels in an elliptical orbit, following a somewhat wobbly path around the galactic center. This path is influenced by the gravitational pull of the galaxy's mass, which includes not only stars but vast clouds of gas, dark matter, and other mysterious components. Throughout its orbit, the solar system passes through different regions of the Milky Way, each with slightly varying densities of gas, dust, and stars. These regions can have subtle effects on the environment of the solar system. For example, when the Sun passes through dense clouds of interstellar gas and dust, it can influence the influx of cosmic rays reaching Earth. Cosmic rays are high-energy particles from space that can affect the Earth's atmosphere and may have links to changes in climate or biological evolution. Further, as the Sun navigates the spiral arms of the Milky Way, it moves through zones rich in star formation. Spiral arms are sites where gas clouds collapse under gravity to birth new stars. Since these regions contain many massive, short-lived stars, they can be hotspots of energetic phenomena like supernova explosions, which release enormous amounts of energy and cosmic rays. However, the solar system generally spends most of its time in the quieter regions between spiral arms, which might help shield the Earth from some of these dramatic events. Besides the radial movement around the galactic center, the Sun also oscillates up and down through the galactic plane by about 200 light-years in a sine wave-like motion over approximately 60 million years. This vertical motion is due to the combined gravitational forces exerted by the mass concentrated in the galaxy's central plane. Crossing the galactic plane exposes the solar system to differing gravitational conditions and varying densities of interstellar matter, possibly influencing Earth's exposure to cometary impacts and cosmic radiation. Scientists have proposed connections between the solar system's galactic motions and significant events on Earth, such as mass extinctions and climatic shifts. These links remain areas of ongoing research and debate, requiring further evidence to fully understand the interactions between astronomical and geological phenomena. Nevertheless, understanding the cosmic year underlines the fact that Earth and life on it are situated within a larger cosmic setting, affected by the broader dance of the galaxy. Scientists use observations of star movements and sophisticated models of galactic dynamics to estimate the length of the cosmic year and the solar system's orbit path. The precise measurement is challenging because not only does the sun itself move, but the mass within the galaxy, comprising stars, gas, dust, and dark matter, is distributed unevenly. Moreover, the galaxy is not static. It evolves and changes shape over time, influenced by interactions with other galaxies and internal processes. One important aspect of the galactic orbit is that it provides constraints on the distribution of dark matter within the Milky Way. Dark matter does not emit, absorb, or reflect light, making it invisible to traditional telescopes, yet its gravitational effects are evident. The way the sun's orbital speed varies with distance from the galactic center indicates that there must be a substantial amount of unseen mass, a halo of dark matter, enveloping the galaxy. Observing and understanding these orbits gives astronomers vital clues about the nature and extent of this dark matter. In addition to supporting studies about dark matter, the cosmic year concept aids cosmologists and astrophysicists in mapping the evolutionary history of the galaxy. Comparing the number of solar orbits with the age of Earth or of various geological periods allows scientists to correlate astrophysical and terrestrial events, seeking to uncover possible influences between them. Because of the immense lengths of time involved in a cosmic year, it's a tool that helps humanity place its own relatively brief history into context. If we imagine Earth's entire history compressed into a single 24-hour day, one cosmic year would last many times longer than that day. This comparison highlights the grand scales on which cosmic processes operate and the scale at which the cosmos unfolds. Our understanding of the cosmic year also deepens appreciation for the nature of time and motion in space. We're accustomed to thinking of the solar system as a self-contained system revolving around the sun. But in a larger frame, the entire solar system is in constant motion around the galaxy, just as the galaxy itself participates in the wider motions of local galaxy clusters and the expanding universe. Ultimately, the cosmic year serves as a reminder that the solar system, the sun, and our very planet are all parts of an intricate cosmic structure. The stars we see in the night sky are not fixed. They are moving objects, components of a dynamic galaxy, orbiting the center of the Milky Way. Our journey around this center is slow on human timescales but immense on cosmic timescales, connecting our local neighborhood in the universe to the intricate gravitational ballet of tens of billions of stars and vast quantities of unseen matter. Understanding the cosmic year expands our perspective beyond our immediate experience, framing humanity's existence within astronomical rhythms that unfold over hundreds of millions of years. This knowledge adds depth to our search for answers about Earth's past, the origin of life, and the galaxy's evolution, linking the fate of our planet to the motions of the sun and stars within our Milky Way. Exploring the concept of a cosmic year also invites us to consider how measuring such vast spans of time challenges and refines our understanding of astronomical phenomena. Unlike a human calendar based on Earth's predictable orbit around the sun, the cosmic year is derived from observing complex gravitational interactions across immense distances. The orbital period of our solar system about the galactic center is influenced not just by the mass distribution within the Milky Way, but also by the presence of dark matter, the galaxy's evolving structure, and subtle changes in orbital velocity. To appreciate this in more detail, it helps to understand that the Milky Way galaxy, like many spiral galaxies, is not a rigid structure. The stars and interstellar material orbit the center at differing speeds depending on their distance from it, a phenomenon known as differential rotation. Stars closer to the center usually orbit faster, while those farther out move more slowly. However, these velocities do not decrease as expected based only on the visible matter within the galaxy, which was one of the earliest indicators pointing to the presence of dark matter. This invisible component greatly influences the gravitational potential in which the Sun moves, dictating our solar system's orbital speed and the length of a cosmic year. Moreover, the path of the solar system around the galactic center is not just a flat circle. It's often described as a rosette-like orbit because gravitational perturbations from other massive objects, such as giant molecular clouds, star clusters, and the galactic bar structure, cause it to shift direction over time. Sometimes, these interactions can slightly alter the orbit's eccentricity, pushing it into more elliptical shapes or changing the altitude of the solar system's oscillations above and below the galactic plane. Understanding the precise motion is of great interest to astronomers aiming to reconstruct the history of our cosmic neighborhood. Another fascinating implication of the cosmic year pertains to the very age of the stars and systems we observe around us. When astronomers chart the motions and positions of stars, including their speeds and orbits, these data help reconstruct the dynamic evolution of the Milky Way itself. By counting how many cosmic years have passed since star clusters formed, or since notable galactic events occurred, scientists piece together a timeline of the galaxy's formation and transformation. For instance, some globular clusters, ancient, densely packed spheres of stars, are believed to be relics from the early days of galactic assembly, dating back over 10 billion years. This timeline corresponds to many cosmic years, showcasing the longevity and persistence of stellar populations amid the galaxy's constant motion. The cosmic year also brings an interesting perspective when applied to broader cosmological questions. Our galaxy is one member among billions in the observable universe, each traveling through space following its own path influenced by both local gravitational forces and the overall expansion of space-time. While the solar system's motion around the Milky Way happens on a scale of hundreds of millions of years, galaxies themselves often orbit centers of mass in larger clusters or superclusters, or undergo collisions and mergers that dramatically reshape their structures over billions of years. Understanding the cosmic year helps us see our solar system as part of a multi-level hierarchy of movements, each with its own timescale. From the brief seconds of atomic processes within stars to the billion-year cycles of galactic evolution. Importantly, the concept of a cosmic year underscores a fundamental aspect of our universe. Everything in space is in constant motion. Although the night sky appears fixed to the casual observer over millions of years, the positions of stars shift, driven by their orbits within the galaxy and gravitational interactions with other objects. The stars that formed the familiar constellations we know today looked quite different hundreds of millions of years ago. And in the future, as the Sun completes multiple cosmic years, the sky will change further. New stars will have moved into view, others will have faded, and the patterns humans have celebrated for millennia will transform. This dynamic nature of the cosmos is also reflected in our understanding of life on Earth and the planet's environment. Some hypotheses propose that the solar system's passage through different parts of the galaxy during its orbit may have influenced life's evolution. For instance, when the solar system enters denser regions of interstellar space, there can be an increased flux of cosmic rays, potentially affecting atmospheric chemistry and climate on Earth. While research in this area is ongoing and conclusions remain tentative, the cosmic year provides a useful framework for correlating terrestrial geological and biological events with the solar system's larger galactic journey. One example of this is the study of periodic mass extinctions. Fossil evidence suggests that mass extinctions on Earth have occurred at somewhat regular intervals, sometimes tens to hundreds of millions of years apart. Some scientists have speculated that these extinctions might be linked to the solar system's galactic motion, such as by triggering a higher rate of comet impacts when the solar system passes through the densely populated galactic plane, disturbing the Oort cloud and sending comets toward the inner solar system. While the links are still under investigation, understanding the timing and nature of the cosmic year helps frame these hypotheses within a coherent galactic context. Technological advances have bolstered our ability to measure the solar system's motion with increasing precision. The European Space Agency's Gaia spacecraft, for example, is creating a detailed 3D map of billions of Milky Way stars, tracking their positions and motions. These data allow astronomers to refine models of the galaxy's mass distribution, including unseen dark matter, and to improve estimates of the cosmic year. As data improves, scientists can better understand the nuances of the solar system's orbit, local gravitational influences, and how spiral arms and other structures shape the galactic environment our system wanders through. The pursuit of such knowledge reminds us that while the cosmic year might seem abstract or distant, it has concrete implications for our understanding of the universe and our place within it. The orbit of the Sun around the Milky Way's center governs the context for the solar system's history, the environmental conditions in which Earth exists, and even potentially the evolutionary pathways of life. It places our relatively brief human experience within a vastly larger temporal and spatial framework. In practical terms, the cosmic year also functions as a time unit for astronomers and astrophysicists measuring slow processes. Much like how geologists use the calendar year to describe Earth's deep history, the cosmic year allows scientists to describe repeated cycles in galactic dynamics, the migration of stars and star clusters, and the timing of galactic collisions. These timescales extend far beyond human history, but provide a crucial backbone for decoding the past and predicting the future of our galaxy. Beyond the scientific implications, the cosmic year enriches our philosophical appreciation of the universe. It challenges the human tendency to think in short timeframes, encouraging us to envision durations that defy everyday experience. 50 cosmic years encompass the Sun's entire lifetime, during which countless processes, stellar evolution, planetary formation, galaxy mergers, unfold. Recognizing the immensity of a cosmic year situates human history within a grand cosmic cycle, highlighting how our planet's story is part of a much larger, ongoing narrative written across billions of years and vast distances. Reflecting on the cosmic year also emphasizes the interconnectedness of astronomical phenomena. The solar system's orbit is shaped by the galaxy's mass distribution, which includes stars we might never see and dark matter whose nature is still a mystery. The galaxy itself is influenced by neighboring galaxies in the local group, as well as gravitational forces acting on grander cosmic scales. Studying the cosmic year thus connects many areas of astrophysics, from stellar physics and dark matter research to galaxy dynamics and cosmology. In addition, the cosmic year encourages us to further explore the Milky Way's structure. Spiral arms, galactic bars, the central black hole, and the halo of dark matter are all components contributing to the solar system's orbit. Each element contributes different gravitational effects that impact the cosmic year's length and the orbit's shape. By mapping and modeling these factors, astronomers can refine our understanding of the Milky Way's architecture and its evolution. For instance, the supermassive black hole at the Milky Way's center, known as Sagittarius A, exerts a strong gravitational pull on surrounding stars, influencing their orbits and the overall galactic dynamics. While the solar system is far from this central point, the combined gravitational environment around the galactic core establishes conditions that ripple throughout the galaxy, affecting the motion of every star and planet, including ours. The cosmic year's immense scale also highlights the role of gravity as the fundamental force shaping the universe. Gravity orchestrates the motions of stars in galaxies, guides the formation of planets around stars, and governs the orbits within star systems. The solar system's orbit around the galactic center is itself a manifestation of these gravitational forces acting over millions of years, providing a direct example of gravity's role on the grandest scales accessible to human observation. Understanding the cosmic year, then, is not just a matter of defining a long orbital period. It represents a gateway into grasping how the universe functions over time and space. It also serves as a constant reminder that our existence, situated on a tiny planet orbiting an ordinary star, unfolds within a context of immense cosmic rhythms and motions. This perspective can influence scientific outlooks, inspiring curiosity and a deeper desire to comprehend the galaxy we call home. As astronomers probe further into the structure and dynamics of the Milky Way, they will continue refining the parameters that define the cosmic year. Such progress sheds light on the complex interplay between visible matter, dark matter, and the dynamic processes that govern galaxy evolution. Moreover, the cosmic year encourages an interdisciplinary approach bridging astronomy, geology, biology, and physics. By linking Earth's history to the solar system's path through the galaxy, researchers seek to understand whether cosmic phenomena have directly or indirectly influenced Earth's climate, biodiversity, or even the emergence of intelligent life. While much remains to be discovered, this synthesis of knowledge stands as a testament to the power of the cosmic year concept as a tool for understanding. In summary, the cosmic year embodies one of the grandest time cycles known, marking the sun's long and steady voyage around the Milky Way's heart. Spanning 225 to 250 million Earth years, it challenges us to think beyond our ordinary sense of time, encouraging us to see Earth and humanity as participants within a much larger celestial movement. By studying this cosmic timeline, scientists gain invaluable insight into the structure of our galaxy, the behavior of its constituents, and the context for our own planetary existence within the universe. This enduring orbit connects the story of our solar system to the broader story of the cosmos, its past, present, and future, and enriches our understanding of the fundamental forces shaping existence on the grandest scales. Ultimately, the cosmic year is a powerful concept that frames the solar system's motion in galactic terms, inviting us to explore questions about the universe's workings, the nature of time, and our own place amid the stars.